Jesus' name, amen. All right, want to just review just a few things about the electron configurations and do a couple of examples that might be helpful for you when you're looking at your homework. And so very simply, doing electron configurations, remember, you need to know how the order of filling occurs. Okay, you can do that by reading it off the periodic table, or you can make the list and use arrows. I don't care which one you choose, you just need to know the order of filling. And then there's different ways that you can look at the filling. And so if I take a look at oxygen, there are 8 electrons. And when I start filling in the 8, Aufbau's rule says start from the lowest level fill up. And so I put 1 here. Okay, in the up position. I have violated no rule. When I put the second electron in, 1 space, I get a rule that applies, and that is Pauli's exclusion principle, meaning that in 1 space, I can have 2 electrons, but they have to be in opposite spins. We designate them plus 1/2, negative 1/2, but we draw that up and down. Okay? And so I've filled 2 electrons. At this moment in time, I haven't drawn oxygen, but I have drawn all the way up to helium. Okay? I still have electrons to go. Have I violated any rule by putting that 3rd electron in? I have not violated any rule. Okay? The rules are I have to fill the next level. That's Aufbau. This is the next one. There's where the 3rd one goes in. I haven't violated Hund's rule. Hund says I have to have 1 in each before I start doubling up. And Pauli says that if I have 2, 1 has to be up, 1 has to be down. There is no convention that up must be the one that goes in. Down is fine. I only have to talk about up and down when I have 2 in the box. Okay? And so normally by convention most people start up. That's just what they do. It isn't a rule. Okay? I could put down. Now, my next electron, how does it have to go in? Up. I'm not at oxygen yet. I am at beryllium. I still have 4 electrons. All right? Have I violated any rule at this moment in time? No, I put 1 in each, right? And I have filled from the lowest level. This is my next level. At this point in time, what must I do? Add 1 facing the other direction. And at this point in time, I have 8 electrons. Okay? When I look at this, I have 8 electrons. This is oxygen. How many unpaired electrons do I have? 2. Okay? Now, I can do it other ways. And if I do vanadium, vanadium is number 23. I can start with 1s and go all the way through. But remember, chemists are lazy. And so we try to take a shortcut. And so what we do is we say, vanadium looks just like argon. And argon represents 18 electrons. Okay? And then what's left? After argon, my next level is 1, 2, 3, 4, where potassium is, 4s, and I put the 19th and the 20th electron in, and then 21, 22, 23. Okay? And that's 23 electrons representing vanadium. This is what you would absolutely predict that would look like. Now, I can be even lazier and write 4s2, 3d3. How many unpaired electrons do I have in this? 3. It's easy to see right here that I have 3, right? You have to think about it when I ask you the question when you write it this way. How many are unpaired? Okay? Now, what I want to show you is this. There is a difference between what we're going to call core electrons, ones on the inside that usually do not react, and valence electrons, the ones on the outside that tend to be the reaction, okay, in what actually happens with the element. And so for phosphorus, the shorthand configuration is neon. It looks like neon plus 3s2, 3p3. Okay? Now, valence electrons are the ones that react. These are the ones that are gained and lost in chemical reactions. All right, here's a definition that most books use. Valence electrons are the s and the p electrons only. All right? Most of the time, we ignore d electrons because most of the time, the d electrons are not the ones that are reacting. So you may write a configuration that has d in there or even f's in there, but those are considered normally not valence. Only in special cases do they react and become. They're usually considered core, the ones that don't react. Okay? So, core electrons, valence electrons. Now, we asked you quite often in the homework, were there unpaired electrons or were there paired electrons? Okay, at the end. And this is, the reason we do this is because it gives a property to the element. If there are unpaired electrons, it is called paramagnetic. That means it actually has the ability to be magnetic. It will stick to a magnet. If there are no unpaired electrons, it is called dimagnetic. And that means it is not magnetic. And so there are some metals in which a magnet sticks to, and there are some metals that a magnet doesn't stick to. This is one of the reasons why it would be either magnetic or not. Okay? And so I wanted to show you why we were asking about that and the definition, paramagnetic and dimagnetic. Okay? Those kind of definitions could end up on an exam, right? And so knowing those is important. Okay, here is a question from the homework. And so it's going to say which ones are allowed and which ones are not. Okay, so you should be able to look at these four numbers, which should represent, in this case they're only showing 3 of them. 4 numbers will designate exactly where an electron is, but we should be able to know the relationship. Okay, for N, when I evaluate that, what numbers could that be? Can it be anything starting at what and up? It has to start at 1 or higher. Okay? And so, for 2, is that 1 or higher? That is good. Okay. Depending upon what the N is going to depend upon what this is. Okay? What's the highest number of the second number, the L number? It has to be N minus 1 or anything below all the way to what number? 0. So if I'm at 2, does 1 work? Yes. The third number is something that is plus L to minus L, meaning that the possibilities of 1 could be minus 1, 0, plus 1. Those are the possibilities. So, based upon this number, is that a possibility? Yes. This is allowed. What about the second? Is this good? 3? Yeah, that's good. Is this good? Based upon this number, that cannot exist. Not allowed. That's totally made up. It just doesn't exist. This number good? This number good right here? Nope. Not allowed. Is this number good? Is that number good? Yes. Based upon this, is that number possible? Yes. Allowed. Okay. Here's another one. All right. This is going to ask you, how many electrons live in these spaces? All right, the more numbers you're given, the less electrons there are. If you're given 4 full numbers, that represents 1 electron, okay? So if I look at this, all right, level 4, okay, 4 does exist, all right? In 4, you have levels possible 3, 2, 1, and 0, okay? Remember, 0 was a what letter? S, and there's 1 space. The space is numbered at 0. The level 1 is called a P. How many spaces are in P? 3. 1, 2, 3, numbered -1, 0, and 1. In 2, what letter was that? D. There was 1, 2, 3, 4, 5 spaces numbered -2, -1, 0, 1, and 2. And the 3 is what level? F, with 7 spaces. That is numbered -3, -2, -1, 0, 1, 2, and 3. So those are available, okay, for 4. I say level 3. Okay, so level 3 is that one. And then I say in -3, this one. And then I say in that level, how many are pointing down that live in that one level? 1. Okay, I'm in level 4. I'm in an F. I'm in specifically -3. And in -3, 2 electrons could live, 1 up, 1 down. And I define the one that's going down. All right, in this one, how many live in the second? Is level 4 good? Is 3 good? Is a -3 available? Is a -1/4 available? How many electrons live in a space that doesn't exist? 0. Okay, let's look at this last one. Level 3, does that exist? Yes. All right, that's the N number. The L number is 2 and 1 and 0, right? The S is 0, that has a level that is 0. The P has 1, 2, 3 levels that are numbered -1, 0, and 1. And the D has 1, 2, 3, 4, 5. It's numbered -2, -1, 0, 1, and 2. Is there anything else that is defined here? No. So that means how many electrons can live in all of this? How many can live here? 2. And how many can live here? 6. And how many could live there? And 10 plus 6 is 16 plus 2 is 18. Okay? What if you got something ridiculous like N is 5? You have L's that are what numbers possibly? 4 and 3 and 2 and 1 and 0. This is an S, right? This is a what? The 1. A P. What's the 2? What's the 3? What is the 4? It is a theoretical G. How many spaces would there be? There would be 9 spaces. Does this actually exist? Absolutely not. We do not have an atom that large, but we have done the mathematics, and we know if by chance we find an atom where those electrons should exist. We just haven't got there. Theoretically, it's available. We just don't have an example. Now, if it was just N5, there's going to be a lot of electrons that are available. It's just a longer problem, okay? But you do it the same way as I did this 3, okay? What if I did N3, and then I said the M sub S is a plus 1/2? So I gave this value, and I gave that value. how would that change that answer from 18? It would be, in the S, not 2 can live there, but only 1, because I designated only the down ones. And instead of 6 here, how many would I have? 3. And instead of in the D's, 10, I would have 5. And that would be 9. So depending upon what you're given will limit what I'm looking for. The more you're given, if you're given 4 numbers, it's 1 electron. If you're given 1 number, you're doing a lot of work to figure out what's there. Okay. Last little example. Provide the 4 quantum numbers of the outermost electron. In this particular case, so neon, 3s2, 3p3. Okay? All right. The 4 quantum numbers for the last electron, that is this one. The primary number is 3. It's in a p. What is the number for p? Is it 2? 3? 1? Okay, I'm all over the place now. It's 1. All right. What? In the 1, I have from -1 to +1, right? With a 0 in there. Where is that electron in? It's in the +1. And what would be the 4th quantum number of this drawing? A 1/2. What is its charge? Its designation? It would be positive because it's an upspin. That last electron that we fill in, its quantum number would be 311 plus 1/2. Okay? All right. Some of that might help for the homework, I'm hoping. All right, the next thing that we're going to do is kind of give you a little bit of information that you can get from the periodic table. Okay? Periodic means they're repeating patterns in the periodic table. And so we're now going to take a look at some repeating patterns where you can predict, using the periodic table only, some properties about patterns. Okay, I'm going to try to teach you 2 different ways in this. I'm going to teach you the trend. That will actually get you the answer on the test. Then I'll teach you why. Yeah. I'm going to teach you why. That's a little bit more complex, and it's good to understand why because that helps you. But if you just want to understand the trend, that will get you the answer on the test. And so we're going to look at a couple ideas, including size, ionization energy, electron affinity, electronegativity, metallic character, and then how each family tends to react. Because every family reacts similarly. And so the first thing that we're going to do is look at size. All right? And so if I look at size, all right, we have some trends. And so the size of an atom increases as I go from the top to the bottom. As I go down, they get bigger. All right? And then as they go from right to left, they tend to get bigger. All right? Now, look at the trend. In this red box here, where all of the p electrons are, except for that one s electron. Look at the trend. That works pretty good, doesn't it? Over here in the alkali and the alkaline earth metals, the trend works really good. Where does the trend mess up? Transition metals. Okay? Oh, there was one other thing I wanted to do. Transition metals. Transition metals don't work quite right. Okay? And in this, the atomic size is one of those things where it doesn't quite work absolutely well. But we're going to tend to have a trend from top to bottom it gets bigger, and from the right to the left, they tend to get bigger. Why? All right. What we're doing is we're battling between two things: how many electrons are there, and the effective nuclear charge. Uh-oh. What is the effective nuclear charge? I described it once before. Do you remember? The effective nuclear charge. That sounds important. Okay. Remember, if I stood you all up and put you to the middle of the room and I sprayed you with a water hose, what was I representing? What does the spray of water represent? What is the nucleus throwing out? Positive charge. Okay. The electrons right next to it or really close to it feel the positive charge a lot. The electrons on the outside feel not a lot of the positive charge. Even though I might have 18 electrons on the inside and 18 positives on the outside, each electron does not feel one full positive charge. Okay? Because there are electrons that shield, the inside ones shield the outside one. And so the outside one doesn't feel the electron as much. So each electron in each level feels a certain level of positive charge or attraction. Okay? And so that's going to play into this. All right? One thing we need to know about the size of an atom. All right? The S's are a sphere, right? That's cool. The P's are dumbbells, right? The D's are double dumbbells, and then one dumbbell with a donut. And the F's are triple dumbbells, and then there's one dumbbell with double donuts. And when you fill in all of these different shapes inside around the nucleus, effectively, the shape of every atom, when they behave in real life, work like a sphere. Now, that sphere inside, we know, has regions that are more dense, regions that are less dense because of these shapes, but fundamentally, every atom takes a physical shape of a sphere. And we can measure the size of that atom by talking about its radius, because we think of it as a sphere. All right? So that's important when we think about this. All right? Why in the world do the atoms become larger as you go down? Okay, look at alkali earth metals. We start with hydrogen. Has one electron, one proton. The electron and proton are 1 to 1. Actually, it pulls that electron pretty close. It's small. As I go down all the way to cesium and francium, how many electrons does francium have? 87. All right, if somebody weighed 1 pound and somebody weighed 87 pounds, who's bigger? The one that has more pounds or more electrons. So going down the row, very logically, if I have more electrons, it's bigger. That's it. That seems to be reasonable. Okay? Now the other one, I said that krypton, number 36, is small compared to potassium that has 18. That doesn't sound right. Okay? All right? And I'm going to show you why in a moment. Let's see what kind of relationship you can think about in terms of this. All right, the size of phosphorus, sulfur, AS and selenium, arsenic and selenium. All right, when we take a look at these, if I compare sulfur and phosphorus, which one is bigger? Phosphorus, because the trend says that way goes bigger. If I compare sulfur and selenium, which one is bigger? Selenium, because I go down. If I compare phosphorus to arsenic, which one's bigger? Arsenic. Okay. If I compare phosphorus and selenium, which one is bigger? Okay, we said as we move this direction it gets bigger, right? And as I move that direction it gets bigger. At this moment in time, we wouldn't know by just the trend. Because one is one over and one is one down, we wouldn't be able to do that. I wouldn't put one on the exam like that. I would put at least 2 in one direction versus 1 in one direction. What about sulfur and arsenic? Which one's bigger? Arsenic. Arsenic is 1 down and 1 over, so it's bigger. So you could make comparisons between 2s for most cases. Okay. Now, why in the world is it bigger? Where in the world did I put this? I thought I put an example. I didn't. All right, why in the world? Okay. Why in the world was one bigger than the other? Let me stop this. Let me add a slide. No, that's not where you do that. Right here. And I'm going to do this. Okay. Why in the world do I say krypton and potassium are 2 sizes? Oh, I don't like that color. That's too light. Let's go dark. Okay. Potassium and krypton. Okay. Potassium looks like this. Looks like argon, and it has 19 electrons, so it has a 4s, 1 electron. Okay. Krypton, on the other hand, looks like argon, and it has a 4s, 3d, and 4p. It has a lot of electrons. Okay. How many electrons does krypton have? It has 36 electrons. Also has 36 protons. Potassium, on the other hand, has 19 protons and 19 electrons. Okay? Now, here's the deal. Remember an effective nuclear charge. I said that there are electrons that shield the outside. These are the ones that shield the outside. The core electrons are the ones shielding the outside. Now watch this. In the nucleus of potassium, I have 19 positive charges. The shielding electrons are argon, which are 18 negatives. And I got 1 lonely electron on the outside. Okay? Compare that to this. 36 protons inside the nucleus of the krypton. The shielding electrons are only 18 because it has the same core as potassium. On the outside, I have 2, 10 to 18 electrons. I have 18 electrons on the outside. Okay? But check this out. Positive charge is going out, and I get a little tiny positive charge on this outside. Because 19 being blocked by 18 blocks almost all of the positive charge. Very little positive charge actually is seen by this electron, so it tends to be able to get away. All right? look here. 36 is a huge positive charge. 36 positive charge sends out a lot of positive charge past the core electrons. So the core electrons tend to see a lot of that charge. If it sees a lot of the charge, its attraction is huge. And so they get pulled in. Okay? All right, it's like this. We got 19 people watching a class of 19, and 18 are all around the teachers. The one little student can get far away on the playground. But if I have 36 teachers watching 36 and only 18 are huddled around, then I can have attention for those 18, but still have a lot of attention for the others, and I can make sure that they keep in. And so the core electrons are the same, blocking for potassium and blocking for krypton, but krypton has so much more positive charge that more of the positive charges gets to the outside. That's why they get pulled in. That's why their size is smaller. Okay? And so that's why the trend happens. Okay? Now, what matters on the test? I will give you 4 elements and ask you which one's smaller, or put them in order. If you know bigger, you're done. Right? But now you understand why. As I go down, I just have more electrons, I have to take up more space. And as I go from right to left, it's an argument because the effective nuclear charge more gets to the outside, so that brings those electrons in. Now, what can you do with the atomic radii? Well, if I want to know what the distance is between 2 atoms when they are bonded together, what I'm really going to do is describe the distance between the 2 nuclei. And so if I take 2 atoms and I know their radius, both of their radii, then I come and I push them together, and remember they're balls, so they get right next to each other. And the distance between the edge and the nucleus on one and the distance between the edge and the nucleus on the other, it's this radii plus this radii, and the bond distance are the distance between the 2 nuclei. If you know the size of each atom, the radius, then you add the radius of one plus the radius of the second one, and you approximate the distance of the radius of the entire atom, or the molecule, the bond itself. Now, that's nice and easy, and this is easy types of calculations. And really, when we do these calculations in real life, the actual bond angles, the bonds are really, really close to our theoretical calculations. Now, there's something weird, okay? We usually measure distances in what unit? What unit do we measure distance in? What? Meters. What in the world is that? That's not a meter, okay? That is called an angstrom. All right, we use angstroms almost exclusively when we're talking bond distances, okay? Why do we do that? We like bond distances between atoms to be numbers like this. 1, 2, 2.5, 3, okay? And so if we change the meters into angstroms, then we get values when they're added together that come up as one number with a decimal. Now here is the angstrom. 1 angstrom, 1 angstrom is equal to 1 e to the minus 10 meters. Okay? Now we have a minus 9 and we have a minus 12. Minus 9 is nanometers. Minus 12 is picometers. All right? But 10 is not in the mix. We only use this in terms of bond distance. Okay? Now, the first slide I gave you had some numbers, and they were in angstroms. But don't use those numbers in the book to do your homework for ChEM-111. Why? ChEM-111 is picky. And it's so picky that you got to use its reference. So where do you find the sizes of atoms in ChEM-111? All right? We got to go to where the pickiness is. And if we go to, not Moodle, cancel. If we go to the periodic table, okay, on this, which gives all the information, which you can't actually see, okay, because of the color. All right, that's not great. All right, here is hydrogen. The atomic radius is in, it says 53 picometers. All right, to change that into angstroms, you place the decimal point at, it's 0.53 angstroms. If I change to iron, that would be 1.56 angstroms. Silver, 1.65 angstroms. Osmium, 1.85. Trying to find a big one. Oh, that one might not. No data. They haven't done that one yet. Bismuth, 1.43. Okay, so you don't have to do. You can actually do a calculation to change them to meters and meters to angstroms, but you can simply convert these very simply to do the problems. But that's where you get the value. If you use the value on the chart in the book, your answers will all come out wrong. You must use the values on this. And remember, if it's 0.00001 off, you get a big red box, right? It is that picky. So make sure you use those. Okay. So the periodic table in ChEM-111 is where you use. And so if you take a look and you're given any molecule, you would look up the, let's say for sulfur, you look up the atomic radius for sulfur and the atomic radius for carbon, and then you would look up on the chart and it would be some sort of angstroms with some sort of angstroms, and you add them together. That would be the distance between the carbon and the sulfur. And you could do that for any two atoms that are put together in a bond itself. And so those questions hopefully should be not too hard. And on the exam, we will give you a reference chart, either a chart of the distances, because the periodic table doesn't have it. I don't want you to memorize the distances for every single element on the periodic table. Okay, that is ridiculous, but you should be able to look it up on a chart. Okay. Last concept in this chapter, I do want to point out one other thing in the other chapter. Formations of charge. All right. Elements can lose their valence electrons to become charged, okay, by losing electrons to become only core. Added to this, they can gain to the next noble gas. Okay, that means here, if I take a look at sodium, sodium has how many electrons? There is 11 total, 10 are core, 1 is valence. Okay. Now, the last row, number 18, are called what kind of gases? Noble gases. Another name for that row, this row right here, it's called the inert gases. All right? If any element is at Disneyland, the happiest place on earth, these are the ones. Okay? They are happy because the amount of electrons around the nucleus is perfectly balanced. It's exactly what we want. Okay? Any element that is away from that has more electrons or less electrons than the perfect numbers. And so sodium has 11 electrons, and the closest perfect balanced number of electrons around a nucleus is 10. Neon represents the perfect balance. So when sodium reacts, it tends to do this. It will lose its electron in the valence shell, and it will be left with 10 electrons, and its electron count will be the perfect number of 10. Its charge would be plus 1 because it has 10 positives. It has 11 positives and only 10 negatives. What about fluorine? How many electrons does fluorine have? It has 9, right? And what is the perfect number? 10. So when fluorine reacts, okay, it could go to this one. It actually has two choices. It can go to 10, or it can go all the way to 2. It has 9. Which is easier? Gain 1 to become 10 or lose 7 to become 2? Gain 1. It will gain 1, and it will become 10 electrons around the nucleus. The nucleus will have 9 positives. It will have 10 negatives, and so it will be a charge of a -1. Okay? Everything is trying to be like, in terms of the number of electrons, the noble gases, because they are very happy. Notoriously, they don't react. Okay? Remember that an ion is when it becomes charged, an atom becomes charged. It has an imbalance of protons and electrons. Remember, chemistry is this, only changing electrons. And so an atom that loses an electron, becomes positive, is called a cation. And when an atom gains electrons and becomes negative, it's called an anion. Any atom that has charge can be generally called an ion. All right. There's one thing I do want to show you before, and I'm going to use the last 5 minutes to do this from the other. I left off one thing, okay, in the other chapter that is an important item for you to know. Okay, I skipped over it. Here it is. All right, when we predict the filling, an order of the electron configuration, all of these are yellow, okay, because they do not follow the rules. Now, where are they located? Transition metals, okay, if you're ever there, they don't follow the rules. They're like teenagers, okay? They sort of do it sometimes, but not all the time, all right? And so, whenever you're predicting something in the periodic table and it ends up either in the transition metals or the lanthanide-actinide series, you've got to watch out. And so, if I predicted chromium, okay, chromium looks like this. Chromium looks like argon, and then it has some more electrons. I would put the 19th here, the 20th there, the 21st, 22nd, 23rd, and the 24th electron, because it has 24 electrons. That is what I would predict following the rules I've been told. But if you look up what happens for real, this is what happens for real. One of the electrons gets promoted from the s into the d orbitals. There is a special stabilization when you have a half full or a completely full shell. And by doing this, I have a full shell and an almost half. By doing this, I have 2 half full shells. This is actually lower in energy. If you would have predicted something that is an S2, a D4, because of stability, it becomes an S1, D5. That is the only rule, one of the only rules that actually makes sense. The other ones are just random. Okay? For copper, I would predict this. Let's see. Okay? Copper has 29. That would how I would fill 29. But for real, what happens? Copper does this. The real full D is much better in energy than having a full S. So if you predicted S2, D9, this one becomes S1, D10 because the 10 full is better than the S being full. These are the only two exceptions to the rule. If you end up doing something in the transition metals or the lanthanide-actinide series, do it like you should, what you predict. And then look up what actually happens for real. Most of them, there's no reason why that I could tell you. There is reasons, but way past what you understand. But at this moment in time, this is what you should understand. If you fill out one in the periodic table, you need to look it up to verify what the real answer is before you hit submit on ChEM-111. All right? The only exceptions I could ever give you that I would expect you to know is if it is S2D4 gets promoted or S2D9 gets promoted. I would expect you to know that one because there is a reason why. All right?